Hi everyone, good morning. Can everyone hear me?
Yep.
Okay, let's see. I have a message here that my headphone isn't working, but yeah. Okay, so let's start. We're still waiting for a few people, but nevertheless, let's start. So first of all, I'm hoping that you all had a good semi-break with the lecture that we skipped, and my understanding is that several of the other classes have done it or will be doing it this week. So okay, so hopefully this also gave you a little bit more time to catch up. Let's see. So let's start with a few administrative things. So first of all, just a reminder that everything is available on the web. Please visit the website because we often get messages and questions despite the fact that I've said it in class or it's clearly stated on the website. So please make it a habit to follow what's happening there. Homework 2. So we extended it until the 22nd. Which is, I guess, Thursday this week. We finished quiz 5 yesterday, and I wanted to say a couple of important things about it. So first of all, almost all of you did it and did well. You can see the statistics here. Okay. Almost all of you did it. So a few people still haven't done it. But almost all of you have done really well. I know that there have been a few questions, but I don't want to attend to this. I do want to attend to one of the questions, and I'm going to use it as a hint for the homework. So one of the key questions that you've had on the homework so far has been about the efficiency of average perceptron. We deliberately didn't talk about it. This is a challenge for you to think about it. I assume that all of you that already ran on the name entity recognition dataset know what I'm talking about.
Hello. Can you still?
Oh, okay, we can hear you now.
Can you hear me now?
Yes.
Okay. Anyhow, so there were questions on the efficiency of average perceptron, and as I said, this was by intention. I mean, we wanted you to think about it. And all I'm going to say, and as I said before, when I was potentially disconnected, all of you that have already ran on the name entity recognition data.
I'm not sure what's happening here. Let me try to work without the headphones and see if that works. Can you hear me now?
Yep.
Yes.
Yes. Okay, thanks. So Let me know if there is any problem, because there's some other problem with the headphones. So here is the hint that I wanted to give you. The hint is in question 4 of the quiz. Read it carefully, think about all the options, and think about why did we ask these questions. And once you understand this, I think it will give you a big hint toward solving or developing an efficient solution for how to implement average perceptron. Okay, so that's a hint. And to move on with this, I want to remind you that we have a midterm, 10/28. So it's a little bit more than a week from today. It's going to be at the class time, and we are going to put today a few old midterms so that you can look at it. But as I said last time, the difference is, given the setting that you're going to sit at home and do it, the questions are going to be somewhat different. They're going to be more quiz styles questions. So not exactly the same style, even though the same material that the older midterms covered. Given that it's going to be at a class time, please let me know if you have a time zone problem. So far, no one notified me, so we're assuming that everyone can be here at 10:30 a.m. Eastern time. Also, for some of you, I have information that you need more time for the exam. Again, please drop me an email so that we can synchronize about how we're going to deal with it. Recording, yes, we are. Any important questions? Will we get instant feedback after the exam? In principle, yes, unless we see any technical problems. Okay, so where are we? So in the last week, we talked about Perceptron with quite a few extensions, and I'm going to highlight 2 of them here. On the right side, we talked about general stochastic gradient descent algorithm, and we showed that, in fact, we can view Perceptron as a stochastic gradient descent algorithm, just like the LMS algorithm that you introduced at the beginning, only with the difference that Perceptron is an SGD relative to the hinge loss. So we kind of close the circle here, but showing SGD as a very general purpose algorithm. 2, we introduced a new stochastic gradient algorithm. Specifically, we introduced the case of adaptive learning rate. The algorithm was ADAGRAD. And again, we discussed how it adapts the learning rate. And I suggest for people that have struggled with it a little bit to go back to the slides and think about the examples that I've given. Play with Boolean examples. Boolean examples are simpler, and it's easier to understand what's happening once you can play with this. Okay, and then we also talked about a few extensions that have to do with preventing overfitting or dealing with, given a data set, given that there are multiple hyperplanes that can separate the data, which one is preferred and how can we do something to prefer H2 over H1. And we ended last time talking about a general way of thinking about this, and this is where I'm going to start today, even though at this point all we can do is just hand wave around this notion. The notion is that of regularization that we've mentioned before. And basically, it's a general technique to force the learner to learn simple functions. So the idea is that rather than just talking about this term, the loss that we talked about before, we are adding another component here, which we call regularization term. And you can add various regularization terms, and I'm giving some ideas here. In all cases, the algorithm is named differently depending on what regularization terms you add. So for example, in the LMS case, the loss function component that we studied is this one, y minus the dot product square. If you add as a regularization term L2 norm of W, so which is written here, we defined it last time. This algorithm is now called ridge regression. If you add L1, which is basically the sum of the absolute values of the components of W, this problem is called lasso. So notice that it's really the same optimization problem almost, with one difference here in the loss function, basically the regularization term. If we are dealing with hinge loss, which we introduced and played with last time, typically people add as a regularization term this L2 norm, sum of squares of the components of W. And in this case, the problem is called support vector machine. We're going to get to it in a couple of weeks. If you deal with logistic loss, which is written here, again, typically people would add the L2 norm, and this algorithm is called logistic regression. So essentially, it's the same problem in all cases, where the difference is that we are dealing with different loss functions, and we are adding different regularization terms. But given that basically what we are doing in all cases, we are differentiating in order to get the update rule, essentially we're solving the same problem every time. The algebra is a little bit different. And we get actually differently behave algorithms that behave somewhat differently. One thing that is still a mystery here is why do you add as regularization terms things that have to do with the size of W, the norm of W? Why do we think that this is a way to control simplicity? And therefore will allow us to generalize better. And this is something that we're going to try to explain as we go, probably in about a couple of weeks. Questions so far?
Hi, Professor. One quick question.
Yeah, go ahead.
How do we code J, Q, and R? So R is, I guess, the regularization term, and Q is the loss function.
Yes, Q is the loss function, R is regularization, and the overall J is typically called the risk.
Okay.
This is the terminology that we used earlier in the class.
Okay, thank you.
Okay, so with this in mind, I want to move to another aspect that has to do with comparing algorithms and understanding what's important. So in the homework, you focused on two families of algorithms, additive update algorithms. We focused on Perceptron, but as we'll see, support vector machines is very, very similar. In fact, you could already see it in these slides, because you know that Perceptron is SGD with hinge loss. And I told you here that hinge loss also drives support vector machines with a slight modification to the objective function here with the addition of the regularization function. But we also talked about a multiplicative update algorithm. We know is one representative that you play with in the homework. And the reason I want to talk about it, first of all, I'm just writing here very briefly the algorithms. This is the top one here is Perceptron that you should already know by heart, right? So basically, we are either adding something to each component of the weight vector or subtracting something to each component of the weight vector. Notice that I'm writing it here deliberately a little bit differently, but think about it and convince yourself that it's the same. I'm writing it now per coordinates of the feature vector. And we know also, I'm writing it per coordinate of the feature vector. We either multiply it by a number if we made a mistake on a positive example, or divide it by a number if we made a mistake on a negative example. Why do I mention it? The reason is that we have a lot of algorithms, and we have to think about which algorithm is better and how to compare them. So because we are talking here only about linear functions, you can say, you know, at the end, all of them are going to be able to separate the data. So why do we care? They can all represent the data. But we do want to know something about how quickly are we going to learn, or various other notions of which algorithm is better. For example, you can think about how many examples are needed in order to get to a given level of accuracy. Or you can think about how many mistakes will an algorithm make before getting to a given level of accuracy. These are not exactly the same questions. You can think about efficiency. How long does it take to learn a hypothesis and evaluate it? Just computing it. You can think about robustness to noise. You can think about adaptation to new domains. All these are issues that homework 2 deals with. And with the key lesson that I want you to be aware that these issues exist. Of course, you're not going to explore it very deeply, but you will play with enough algorithms and data sets at least to allow you to realize that these issues exist. And I want to highlight a few issues here. So one thing that people often do not realize that one of the key issues that plays a role here is the data itself. What types of data are you learning from? Some characteristic of the data. And I'm going to highlight one characteristic of the data that is really important and give some examples. So let's assume that we're dealing with the problem of context-sensitive spanning. In many respects, very similar to the NER problem that you are dealing with. So there is a question on the chat on does multiplicative weight algorithm essentially give greater importance to each observation or training example? So it's not quite that, but they update the weights in different ways, and I'm going to get now to what is the significance of that. But again, the significance depends on the type of data. So let's assume we are looking at this problem here, context-sensitive spanning correction. I don't know whether to laugh or cry. Hopefully some of you noticed that I have a context-sensitive spanning mistake here. I should have used this kind of weather. And how do we address these kind of problems? Just like the way you address the NER problem in homework 2. You define a set of features. Really, features are relations that hold in the sentence. So you could think about it. What happens before the word no? What happens after the word no? What happens before the word whether? What happens to words to the right of whether, and so on. And once we decided on a set of features, we map the sentence to its feature-based representation. So this feature-based representation gives some information about the sentence to the learning algorithm, not all the information. For example, in many cases, some order information is disappearing just because the designer of the feature set decided that maybe it's not that important. But once we map this sentence to its feature-based representation, we use this as the input to the algorithm. Now, really, if you think again about what you've done in the NER, there are two steps in coming up with feature-based representation. The first step, what is the information sources that are available? We are looking at words, order of words, maybe properties of the words. Remember that in the badges example, you wanted to also look at, is this word a vowel or not? You may want to look at positions of the word relative to the target word on which you want to make a decision. But in addition to the information sources, we also think about what features to construct based on this. The features are not necessarily identical to the information sources. And one question here is, why do we make this distinction? Why is this distinction needed? Anyone wants to comment on that? Think about the features you used in the NER. You did not just use the sources, the information sources themselves. We ask you to use conjunctions of them. Why is that? So conjunction is a non-linear function that provides expressivity to the function. Some function that, if you learn a linear function as we do here, some functions cannot be expressed if you just use the information sources. But once you add non-linear components, you are going to be expressive enough to learn the function. That's basically what we are doing. So you can think about this picture that we've seen before. We have a very complex separation here between whether and whether. I'm writing it here as a very complex Boolean functions because the features that you deal with are Boolean features. And if we invent new features, for example,
I think we lost sound again. I can't hear you.
Hello?
Oh, I can hear him. I've heard him.
I can hear him as well.
I can hear.
Okay, thanks. So
then just my audio. Let me see.
So the consensus here that you can hear me. So let's go on.
Sorry for interrupting. Yes, it is just me.
Thanks. So the consensus here is, what's happening? Okay, that's the picture that I wanted to show, where we are basically starting with a very complex decision function, and by inventing new features, we can move to a simpler decision function over the new feature space. Here's another example that we've played with a few times, where I'm blowing up the feature space and I'm simplifying the functional decision. So this is basically what we are doing here. But when we do this, we have to think about the resulting characteristics of the domain. So we're going to get a large number of features. The dimensionality of the feature space is very, very large. In the case of name entity recognition, you have something like 200,000 features because it's a function of the number of words in your vocabulary and more because of the conjunctions. But the instance space is very, very sparse. Right? So most of the features are not going to be active in a given example. At the same time, the decisions really depend on a very small set of features. Most of them do not matter. You just don't know which matters and which do not. So the function space is also sparse. Now, this terminology is really important, and you really need to understand it. Instance space, this is the X. Function space is the hypothesis space. It's also very sparse in the sense that the functions that you care about depend on a small number of features. And of course, we want to learn quickly. We want to learn as a function. We want to learn quickly relative to the dimensionality. And the question is, how do we do this? So I just want to make one comment here that people often ask about. Is this still an issue when we deal with deep neural networks? And the answer is yes. This problem does not disappear, because in many respects, you can think about a deep neural network as the feature extraction of the learning algorithm. And on top of it, in the last layer, you're learning a simple functions, kind of like the linear functions we're talking about. So deep neural networks are doing for us the feature extraction, and we're going to pay for it, and we're going to pay a lot by training time, because they're searching a lot to find what are the appropriate features. So we're going to talk about this more later, but at this point, I just want us to attend to the fact that these issues of sparsity are really important. Now, I'm not going to, the next few slides deal with a little bit of math and quantifying the issue of sparsity in the sample, in the instance space and the feature space. I'm not going to attend to it. If you do want to do it, look at the details here. Instead, I'm going to just get to an example. Not this example. This example, again, please feel free to look at it and understand what's happening. I'm going to get to another example, which is a little bit similar to what you have in class. So basically, what I want to emphasize here is that as a function of the type of functions you care about and the type of data that you're looking at, learning curves for different algorithms are going to look very, very differently. So I'm showing here a function that we've already seen in the class. The function is 10 out of 100 out of n, which means the dimensionality is n. Only 100 out of these n variables are important. We don't know which ones. And if 10 of these 100 are on, it's a positive example. So hopefully you understand that. And what I'm plotting here is, as a function of n, the dimensionality, how many mistakes will each algorithm do until convergence. So instead of showing you this here, I'm going to move to a piece of code that we are going to make available to you. So I'm not going to run all of it now. I'm just going to go over it. So this is a notebook that you can play with. Well, we have some setting up here. And then we have several algorithms. Perceptron, we know average perceptron. Now, the average perceptron implementation here is the inefficient one. You can actually run it and you'll feel that it's inefficient. And then we have mistake bound plots. I'm not going to run it now because it's going to take time. And there are two types of plots that I want to show. One of them has to do with, I want to look at how many mistakes an algorithm is going to make before it converges. If you look at the code, you will see that I define here converges here as 85%. This is the accuracy threshold. So I'm running, we know perceptron and average perceptron. And every epoch, I'm testing how well are they doing, and I'm going to stop when they reach 85%. And I'm going to count how many mistakes they've made before they reach that. So I added some print statement here, just that you'll see what's happening. And here are the graphs that you can see. Again, the x-axis here is the dimensionality, so it's different functions. It's 10 out of 100 out of n, where n is the x-axis. What you can see here is that average perceptron is the orange one, green is perceptron, blue is Winnow. And you can see that for these type of functions, Winnow makes a lot less mistakes. So when they get to 85%, for example, for 400 and 400, the function is 10 out of 100 out of 400, Winnow makes 700 mistakes before it reaches the accuracy we want. Average perceptron is going to make about 1,000. And in general, Winnow is going to scale logarithmically in n, and the other two algorithms are going to scale linearly in n, which is a huge difference. So that's one type of learning curve. It's not the learning curve that we ask you to plot in the homework. The other one that we ask you to plot is a different one. And it shows here. So here I'm looking at as a function of the number of mistakes. So now the x-axis is the number of mistakes. I want to know how many mistakes are being made until we reach, in this case, the accuracy that I'm trying to get to is 95, I think. Let's see here. Yeah, I'm pretty sure it's 95. And what you see here is, again, differences between algorithms, but different types of differences. So if you look at the beginning, with a small number of mistakes, in this case, unfortunately, the colors are different. So the yellow one, orange one is Winnow. You can see that Winnow reaches the 90-some% very quickly with a few hundred mistakes. On the other hand, if we stop here at, let's say, 1,000 mistakes, you can see that Winnow is already at around the 90%. Average perceptron and perceptron are not doing so well yet. They are at 75%. So very quickly, Winnow got to reasonable performance, but later on, to get from the 92% to the 95% that I want, it takes it a long time. It basically stable here, but just below 95%. On the other hand, average perceptron reached around a little bit over 2,000 mistakes, already got to the 95%, no need to learn anymore. Perceptron took a little bit more time to reach the 95%, no need to learn anymore. Winnow is still learning. So you can see different characteristics of different algorithms as a function of, I gave it a specific family of functions here to illustrate this. For other functions, the behavior is going to be different. Okay, there's a third class of algorithms that I want you to be able to play with here, and we've added SGD with various loss functions. Again, I'm not going to run it now, but I want to show it to you. So it's the same type of curve that I showed before, only that now the x-axis is number of examples rather than number of mistakes. And I could ask you why. Hopefully it's clear to you that the algorithms I discussed before, average perceptron, Winnow, are mistake-driven algorithms. So I can ask the questions, how many mistakes are they making? Or plot curves as a function of number of mistakes. The SGD algorithms in general are not mistake-driven, right? So I'm showing here SGD hinge, SGD logistic, and SGD LMS. You can see what the loss functions are doing. And you can see that, again, they behave differently. LMS, which is the green curve, reaches a reasonable performance of 90-some% very quickly, much quicker than the others. The second one in this case is the hinge loss, which is kind of like Perceptron. And logistics is actually the worst in this case. Again, a specific type of function and a specific type of instance space, but you can see differences. Okay, so this is going to be available on the website, and you can play with it. And as I said, notice that the implementation of average perceptron here is the inefficient one, and you'll feel it. You'll have to wait until it finishes. Questions on this?
Professor, can you explain why the SVM is a kind of, the hinge loss is kind of SGD algorithm?
I'm not sure I get the question, but let me try to rephrase it. Hinge loss is a loss function. SGD is an algorithm that takes as input a loss function and computes the gradients and uses the gradient to compute the update rule. So basically, by definition, SGD is an algorithm that takes a loss function. You can give it various loss functions. We started by giving it LMS as a loss function. But last time, I also showed that we can use hinge loss as a loss function. We derived the gradient and showed what is the update rule that is induced from this loss function. We actually showed that the induced update rule is the Perceptron update rule.
Okay, gotcha. Thanks.
Other questions? Okay, no other questions. So basically, the lesson I want you to get here is the lesson of algorithms are different, but quite often they are different because of the data we look at. And again, this is one of the key lessons that I want you to get from homework 2. Okay, so basically, this curve is the curve that I showed you how to generate in this notebook. Okay, to summarize what we've done so far, we introduced multiple versions of online algorithms. Most turn out to be stochastic gradient descent algorithms with different loss functions. The reason I say most is that we know is actually not a stochastic gradient algorithm. It's something that is called exponentiated stochastic gradient algorithm. I did not give the general form of the algorithm, but again, people that are interested could look this up. And we basically suggested a generic improvement or a general form of an algorithm where we have a component that has to do with minimizing the error. This is the loss, right? Summing up over all the examples of the loss, plus a component that basically forces simple hypotheses. And we still don't know why this forces simple hypotheses, but that's what it does. One form of regularization that we've seen is average perceptron, which by itself, by averaging, is a form of regularizations. But we're going to see a more general way to justify why this makes sense. We also talked about adaptive learning rate via undergrad. And that summarizes this part of the class. The last comment I've made is that of the dependence of the function space, the dependence of performance on function space and instance space and their properties. Okay, so what I want to move on to do now is to think more about nonlinear target functions and how can we deal with this. And this is going to be the study of kernels. Any last question on this summary before we move on? Okay, so the picture we're going to have in mind now is this one, the fact that functions can be made linear. We started with this example weeks ago, where sometimes we have data that is not linearly separable, but by changing the feature space, this is an example, this shows that it's not linear. Changing the feature space, moving from x to x comma x squared makes it linear and linearly separable. Here's another example like that. So we have positive example inside these ellipses, the green points, a negative example outside it. And I want to be able to learn this function. Now, you can all agree with me that this is the function here. F of x is 1 if x1 squared plus x2 squared is less than 1. But my toolbox only contains linear functions. That's what we know how to learn well. So I need to change the feature space. And in this case, I'm going to change the feature space by turning it from the original feature space, which has x1 and x2, to the x prime feature space that has x1 squared, x2 squared as the features. And now, when I'm plotting again the same data, that's what I get, right? So the green points become this region here, where the x-axis now is x1 squared, the y-axis now is x2 squared. And therefore, I can separate it now with a linear function. That's what we want to do now. So in order to deal with it, we're going to introduce two concepts. One of them is the dual representation, which in some sense you already know, but we're going to make it a little bit more explicit, and the notion of a kernel along with the kernel tree. Really, the key question we're asking now is how to systematically transform the feature space, how to systematically move from this case to this case. So let's go back to Perceptron. And now this dual representation in kernels can be addressed and be taught in the context of multiple algorithms. In fact, typically people teach it in the context of SVM, and we're going to go back to it when we talk about SVM, support vector machines. But I think it's much simpler to understand this in the context of Perceptron, and therefore that's what we're going to do. So going back to Perceptron, that's what we have to play with, right? So we have a collection of examples. I'm going to think now about the examples as Boolean examples. Think about your NER homework, just because it's simpler. And the learned hypothesis is a weight vector in Rn. So this is the function we're learning, right? The sign of the dot product. And you all know this already. This is the Perceptron update rule. So let's imagine the following scenario. I'm starting with W as my initial vector. I'm observing these 4 examples: positive, positive, negative, negative. And I'm making mistakes as we go on the first one, the second one, and the fourth one. Okay? Now the question is, what is the resulting weight vector? Here's a question for you. I observed with Perceptron these 4 examples. I made mistakes on x1, x2, and x4. what is the resulting weight vector? And for simplicity, let's assume that the learning rate is 1. So you should be able to write down the new weight vector. And let's give you a little bit more time. Okay, still most of you have not responded, so think a little bit about it. It's a perceptron. We know what happens, we know what the update rule is. So once you know what mistakes you've made and what examples you've made mistakes on, you should be able to write down the perceptron update rule, and as a function of it, figure out what's going to be my new W. Okay, I don't want to assume that this is too challenging a question. Once you've implemented Perceptron and ran with over a few examples in the quizzes, okay, let's see what you guys think. Okay. When you say unsure, you mean that it's not known, or you have no idea how to update, how to compute W? So, okay, this is the first time I see an example, an answer that is correct. This one here, where W is a function of the old W and the X's. And all the others that have written answers ask me a question. Why isn't not clear here? I only got one correct answer so far. This example.
So we're assuming that the original weight is 0000, right? So is that?
No, the original weight is W.
Right. Okay.
But it's okay. This example, this answer here assumes that it's 0. It's also fine. But in any way, an example like a vector here is just wrong, because you don't know what x1, x2, x3, x4 are. They are vectors themselves. Is that clear? So okay. So let's look at this answer here. I want this answer that says -1, 1, 0, 1. Why is this wrong?
I think people who wrote that probably didn't realize that X's were vectors, because the labeling isn't really clear. It shows up, like in this format instead of the regular format. Like instead of showing it as a superscript or a subscript. So they probably thought that X1, X2, X3, and X4 were part of one vector X.
Okay, but let's read what's written here at the top of the screen.
So, I mean, my question is though, okay, so I get the math, it's just, and I know that W is a vector, but if I have no initial weighting, then how do I know it's 0? Like what makes it 0?
What makes what 0?
The updated weight vector, an element in the updated weight vector.
It's not 0.
Okay, so let's just read the question again. Let x1 comma plus x2 comma plus x3 comma minus x4 comma minus be examples. What does that mean to us?
It means they're examples within the features.
Just a second. So what do you mean examples within the feature? They are examples. What is an example?
I mean, values of features and a result, y.
Which means x1 here is a vector.
Okay.
X2 here is a vector, right? Is that clear to everyone?
It's more clear now.
Otherwise, I would not call it an example. And I would not associate it with a label. Okay? So these are examples. I don't know what the examples are. In fact, I don't even know what the dimensionality of the examples is. But I know that these are examples. And therefore, these answers that give me vectors here are just in a different space. Okay? Now, whether you know the initial W or not, I actually gave the initial W, but I didn't write it here. You can assume that the initial W is the 0 vector. But even if it's in the 0 vector, it has to be clear that the only solution that we can take here is something of this form, a sum of examples. So let's go back to this. Because if we don't get the notation here, that something is wrong. So what is the notation here? X is a vector of dimensionality capital N. That's what's written here, right? W is a vector of the same dimensionality. That's the game we're playing here. The function here is a dot product between them and the sign over this. And when the perceptron is being updated, this is a vector. This is why I boldface it. I boldface all the vectors. W is the sum of the previous W added X with some constant. The constant is the label Y times a learning weight. So this is all vector calculus. Okay? Now, when I give you examples, it has to be clear that this example has dimensionality capital N, as I'm saying here, this example the same, and so on. And I made mistakes on this. And when I ask what is the resulting weight vector, is the question clearer now? Is it clear that what you have to do is you have to start with your W? What happens when you make a mistake on X1?
You have to update your weight vector.
And how would you do that?
I mean, using that formula.
Which means what will be the resulting weight vector after the first mistake?
Add X1.
It will be just take W and add X1 to it, right?
Yeah.
Once you made a mistake on X2, you're going to add X2. X3, you don't make a mistake. X4, you made a mistake, and then you're going to subtract X4. Okay? So again, I'm not going to ask you to do it again, but this is an acceptable answer because maybe the assumption was that the initial weight vector is 0. So you add x1, you add x2, you subtract x4. Or this one, W old plus x1 plus x2 minus x4. This one is not an acceptable answer because I have no idea why is this true. Who says that the dimensionality is 4 here? The dimensionality is 200,000. So hopefully this is clear. And let's move on. So this is crucial for us to understand this. Please ask a question if this isn't clear at this point.
Wouldn't there be a set of parentheses because the W is updated each time? So it'd be W0 plus X1 parentheses, then that plus X2, and then parentheses. Oh wait, I think I answered my own question. Sorry.
Yeah, we can drop the parentheses. It's all addition, right? So so that's the new W. And really, so first of all, hopefully you understand the algorithm, maybe better now, and go back to your implementations and verify that you understand the algorithms. And the important point I want to make here is that the weight vector is really a linear combination of examples. Right? That's what we see here. In general, I can write it this way. W is a linear sum of the example, x superscript I, with some coefficients, which is a number. Again, boldface means a vector. Without bold, it's just a number. Yi is the label of the xi example. Alpha I is some coefficient. We'll get to it in a second. And R is my learning rate. What is the alpha I here? Alpha I could be 1 if I made a mistake on this example, 0 if I didn't. Because example that I did not make mistakes on do not contribute to W at all. I can put 0 for these alpha i's. So basically, alpha I is the number of mistakes made on xi. If I made 0 mistakes, it's going to be 0. If I made 7 mistakes, which is also possible, because if I've seen the examples over and over again, I could make multiple mistakes on the same example. Again, this was a question in the quiz last time. So, is that clear?
I'm good.
Okay, so now notice this is W, but we actually don't care about W. We care about the decision, right? This f of x, how do we predict? So let's make it a little bit more complex. We care about f of x, which is the dot product of W with x. And I'm going to use this notation now to compute f of x. So what is f of x? Is take this expression, dot product with x. Now, again, this is a linear sum. Dot product is linear, so I can just say linear sum of the constant, which doesn't matter, times the dot product between xi and x. Where again, xi's are the examples I've seen so far, and x, the blue one, is the example I have now and I want to predict on. Again, I know what is W so far with all the xi examples that I've seen. Now you give me a new example, the blue one, x, and you ask me, okay, how are you going to predict on this blue x? And I'm going to take W, multiply it, dot product it with x, and tell you how I'm going to predict, right? In order to do this, I'm just copying the W that I derived here and doing a simple algebra, taking the constants out of the dot product, and that's what I got. So essentially, you can tell me now the prediction is a linear sum of the dot product between the old xi's, those that you've seen in training so far, and the current one on which you want to predict, right? That's what's written here. Okay, so that's the dual representation, right? The fact that I can write the prediction without any w's, just as a function of all the x's that I've seen so far. It's dual in the sense that rather than work in the w space, I now work in the x space. Okay, so this notion of dual space and representing the model, the predictions in the dual space is going to allow us to use the notion of kernel. So kernel is a method that will allow us to run Perceptron on a very large feature space without incurring the cost of keeping a very large weight vector, right? Because the feature space, the dimensionality of the feature space really determines the size of the weight vector and how many weights do you have to update every time, as you can see in your implementation for homework 2. And it turns out that with a little bit of a trick, we can actually compute the dot product in the original feature space before we blow it up to be a very high dimensional space. Now notice that this trick that we're going to get to only pertains to efficiency. It doesn't change the classifier at all. The classifier is going to be identical to the one that you will get if you work on the huge dimensional space. And it doesn't change generalization and so on. It just pertains to efficiency. And as I said earlier, kernels were popularized by support vector machines, but many other algorithms can make use of them. And also in the literature, you will sometimes see the notion of linear kernels, which basically means no kernels, just stay in the original feature space. Sometimes a little bit confusing, but that's the terminology people use. Okay, so we want to get a little bit deeper into these methods. And I want you to have in mind the example that, one second. Okay, so let me start with this. Example that you have in homework 2 for the NER. Recall that you added conjunctive features, right? So you sit on a word and you look at the word to the left of it and you look to the word to the right of it, and you added a feature which is a conjunctive feature. The word to the left of me is D, the word to the right of me is no. And so on. And of course, there's a huge number of features like that because it scales with the size of your vocabulary. But this is a conjunctive feature that is more expressive than just taking the word to the left of me or the word to the right of me. So what I'm going to do here is I'm going to use the same thing, only that I'm going to do this systematically. But rather than just adding conjunctions of a small size, I'm going to add all possible conjunctions. Technically, it's going to be a little bit easier. And it's going to, because it scales so fast exponentially, it's going to also give us a good lesson. So that's the game we're playing now. We are adding conjunctive features, just like you added in the homework. But as I said, I'm going to deal with all the conjunctions. Okay, so I'm starting with this function, which is the dot product between W and X, and I'm adding all the conjunctions. So I'm denoting conjunctions here by T, T1 up to T something. I'm calling it either monomials or conjunctions. and I is going to be the set of all these monomials. So now I'm going to write the function as the dot product over this new x, which is really the monomial over x. Example, if the conjunction is x1 and x2 and x4, and the example is 1, 1, 0, 1, 0, this conjunction over this x is 1. Why? Because x1 is on, x2 is on, and x4 is on. So that's the value of the conjunction of this example. On this example, if the conjunction is x3 and x4, its value on the same example is 0, because x3 is 0, and so on. So essentially, I transform the feature space to a much, much larger feature space. And just like you did when you work with decision stumps, you took the original x, you had 100 decision stumps, and you computed the value of each one of them on x, on each one of the examples, and you derived a new feature vector of size 100. That's what I'm going to do here. I'm taking all my t's, all my conjunctions, and I'm transforming from the x space to the t space, or in fact, I'm going to call it the capital I space. Okay? And I'm showing you an example of this conversion. And again, just like the NER, or if you want the decision stumps, that's what we were doing here. Okay, so now I have this new function space, new function, that is written as linear sum wi's over the ti's, only that the dimensionality here is much larger. So it's not the same. This n here is not the same as this capital N here. In fact, you know how large it is. It's going to be 3 to the capital N, because, in fact, 2 to the capital N, because I'm only using monotone conjunctions here for now. And now I'm running the same perceptron, only on the new feature space. Of course, this is going to give me a great increase in expressivity. I can now express a lot more functions, in fact, all functions. I can run the algorithm, but of course, because I have much, much higher dimensionality, it's going to take me longer to converge. Because every example now has a huge number of features, a huge number of monomials. Okay, but let's see what happens. How do we run it? Again, I'm just showing this picture to show that that's what we are really doing. So I want to go to start talking about these kernel tricks that we are going to do. So we are running Perceptron on this new feature space. And I want to again look at the value of W, just like we looked a few minutes ago. What happens to W? So how do we update W? We update W by adding to it an example or subtracting an example. The example I'm going to call now Z, a typical example. And this example makes additive contributions of plus or minus 1 to some of the coordinates of W. If you disagree with this statement, let me know now. This should be clear, right? It does not, every example that we made a mistake on, Z, makes contribution to some of the coordinate of W, not to all of them. Because if the coordinates of Z were 0, the corresponding coordinate of W are not going to change, right? Only coordinates of W that correspond to on terms of the example, that is Ti of Z is 1, are being updated. And of course, the value of W is determined by the number and the type of the mistakes. so let's just write this explicitly. In order to write it explicitly, I need to know what examples I made, what positive examples I made mistakes on, and what negative examples I made mistakes on. So I'm going to denote by P the examples on which I promoted. That is, these are positive examples I made mistakes in, so I added something to the weight vector. And D are those on which I demoted the weight vector. I subtracted something. And the set of all examples on which I made mistake is just the union of this. So I'm claiming that I can write this function in the following way. So I have a sum over all my features. I is the set of all features. And let's look at what's inside here. So basically, I'm adding 1 for all the examples in P, the positive examples on which I made mistakes, such that Ti of z is 1. And I'm subtracting 1 from all those examples in D on which Ti of z is 1. Okay, so that's basically the new Wi that I have, right? So think about the ith coordinate of W. I added to it ones a few times, and I subtracted from it ones a few times. When did I add 1 to it? On all the examples in P that the ith component of them was 1. When did I subtract 1 from it? On all the examples in D where the ith component was 1. So basically, I replaced the Wi here with this big sum inside the brackets. And now I'm just denoting it differently. And let's see in the next slide, what is my notation here? Oh, okay, so I'm copying this again. This is the replacement for Wi inside these brackets. Now, what do I have here? Think about it this way. So I have a sign outside. I have the sum of Wi outside. And now I'm summing over all z's in M, which is the union of P and D. S of z is just 0 or 1, right? So it basically tells me, minus 1 or 1. It tells me whether I should add something or subtract something, whether I made a mistake on a positive example or a negative example. And what I have here is Ti of z. Now, if Ti of z is 0, I add nothing to this. So the dot product here is going to be 0. If Ti of z is 1, then I do add either the 1 or the minus 1. So Ti of z times Sz is giving me exactly what I want. So essentially what I did here is I just invented the following notation, Sz, which is plus or minus 1, depending on whether it's a mistake or negative or positive, and the rest is just algebra. Yes, conjunction is logical end. And again, this is something we've seen already several times, and also in the homework where you had conjunctive features. Questions on this expression?
Professor, I have questions. So when you write the formula like this way, it looks like you have already know which example it's make. For example, if the training data set have the 5 instance and the 1, 2, the first, the second, and the fifth, you make mistake. So then you will update the weight based on these 3 instance, right? So you can write the formula in this way. But my question is like the weight should be updated immediately once you make a mistake. But this formula looks like you update 3 mistake example at one time.
What I'm asking you is, let's assume that this is the sequence of examples that you processed. And let's assume that these were the mistakes that you observed as you process the sequence. Eventually, what is the W?
It should be minus or add the mistake example.
So exactly. So basically, eventually, the weight vector is adding all the examples in P,
yes,
and subtracting all the examples in D. Do you agree with that?
Yes.
And that's exactly what I'm writing here, only that I'm writing it here inside this linear sum expression of the dot product. So I'm asking, what is Wi, the ith coordinate of W after you've seen these P mistakes and D mistakes? And you should think a little bit about it carefully, and you will see that what happens is this Wi is added once for all the elements in P, where the ith coordinate was on, and is subtracted 1 for all the elements in D for which the ith element was on. And what you want to do to convince yourself, take a few examples, take W, write it as a vector, take a few examples below this, and try to add and subtract to update the W, and convince yourself that this is what's happening.
Would it be an incorrect assumption to say that the promotions and demotions are correlated to false positives and false negatives in your predictions?
They are corresponding exactly to the mistakes that you've made. Yes. I don't want to call them false positive and false negative because I feel that this term is a little bit confusing. You promote the weight when you made a mistake on a positive example. You demote the weight when you make a mistake on a negative example.
Okay, that's clear.
Professor?
Yeah.
Could you explain a little bit about the union between P and D and its relationship to our definition of T, which is the conjunction between features?
No relation at all.
Okay.
So P is a set of examples on which we promoted. D is a set of examples on which we demoted. The union of them is a set of all examples on which we made mistakes. Right? That's clear?
Yes, okay. Yep.
It has nothing to do with the features. This is just examples. Examples are vectors.
Okay.
Okay?
So constructing the whole set for Z. Okay.
And at this point, we don't need to think about the features. The features are going here, where I'm telling you, you know what, rather than just add the whole vector, which is what I'm doing, I'm going to explain it to you at the level of what I've done to the ith coordinate of W. What have I done to the ith coordinate of W? The ith coordinate of W was added 1 a few times and was subtracted 1 a few times. Okay?
Yep.
So forget now the conjunctions. The conjunctions are just the features that you have. The important thing here is that I've added to Wi a few ones and I subtracted from it a few ones. When do I add to Wi? I add to Wi when the example was in P and its ith coordinate, this is the ith coordinate of the example Z, was 1. When did I subtract 1 from WI? When the example was in D and its ith coordinate was 1. That's the thing you have to convince yourself of. And I think I'm going to stop here. And I feel that, you know, all of you that have sometimes difficulty following the math notations should spend time on it. You can even go ahead, because I'm going to continue with this next time, so that you get familiar with the notation and convince yourself of what's being written here and come prepared to ask questions. I still want to ask a question that I was planning to ask, even though we're not there yet, which is this one. So we're going to finish the class with this and get some idea of how are we moving. Okay, almost all of you have answered already. Okay. Okay, that's helpful. Gives me an idea of where we are. I do request, as I said, please go over the slides. Everything is there on the website. You can go over it and clarify the notation to yourself, because sometimes if you see it for the first time and you're still struggling understanding what is a union and what is a conjunction, it takes time. So be ready, and we're going to continue with this next time. Okay, thanks a lot. See you on Wednesday.
Thank you.
Thank you.
Thanks.